Welcome, everyone. So in this section, we are going to solve equations now. We've talked about exponentials and logarithms and how they are inverses of each other. And we've discussed each one at length, properties of each, the graphs of each. And now we're ready to solve equations, which might possibly include, using some of those properties that we've learned earlier. So here we go. So for both logarithmic equations and exponential equations, we're going to have this equivalence property. So here is the equivalence property for exponentials. Given a, x, and y are real numbers with a positive and a not equal to 1, if a to the x equals a to the y, then x must equal y. And this is kind of obvious, if you think about it. Let's say you have something like this set up. I mean, the only way that these two equations are going to equal each other is if the x is 3. And that's basically what this is saying. As long as the bases are the same, then you just set the exponents equal to each other. So you can kind of think like, okay, who cares about the 2's? Okay, and we know those are equal. So now let's go in and make the exponents equal. All right, so let's use this to solve some equations. So they won't be as simple as what I just showed you. We are going to have to do some rewriting quite often to make them the same. So as you're going through and you're trying to solve any exponential equation, this is the simplest method. So you might want to ask yourself, can I write these with the same base? Okay. And maybe it's not common knowledge that 2 to the 5th is 32, but let's just kind of start multiplying some 2's and see what can happen, right? 2 times 2 is 4. 2 times 2 is 4. And 4 times 4 is 16. Well, I can see that if we just had one more 2 tacked along, right? One more 2, that this would make 32. So if we count up the 2's, 1, 2, 3, 4, 5 of them. So we can rewrite the equation, the 32 piece, as 2 to the 5th. And this is the goal, to get them to where they have identical bases. So now that the bases are the same, we can just set the exponents equal to each other. The bottoms already equal each other. So now we just need to make the top, the exponents, equal each other. And then we'll solve this in the usual way that you've been solving all semester. Okay, sorry for the glitching on the board here. All right, so we've got 3x equals, just see if I can get it to stop glitching. There we go. Equals 12. And then we'll divide by 3 to both sides. And we get x equals 4. All right, let's keep practicing this because some of them are a little bit trickier than others. Okay, so for this one right here, one thing that I want to make sure that you remember is a property of exponents that says when you have a power on a power, so an exponent on an exponent, that you just multiply those two by each other to get the new exponent. Okay, and that could be obvious if you write this out. This is really x squared 3 times because it's cubed. And so there's 2 x's for every x squared, right? And so if you count up the x's, 1, 2, 3, 4, 5, 6, there's going to be 6 of these. Okay, so an exponent on an exponent becomes multiplication. All right, so I'm going to rewrite these with the same base. Now 8 can be rewritten as 2 to the 3rd. And 4 can be rewritten as 2 to the 2nd. So here is where we have an exponent on an exponent. So what we're going to do is we're going to take these 2 exponents and we are going to multiply them by each other. You might see me skip this step in the future, but I thought it was important to mention it because it's going to come up later too. So it's really important that we remember when we have an exponent on an exponent, we multiply. Okay, the bases match, so we can just forget the 2's. They already match. Let's go in here and make these exponents equal each other. So we're going to go ahead and distribute the 3 in. And then we'll distribute the 2 in. And then we'll solve. So I'm going to move the smaller variable to keep things positive. So 3x plus 4x is 7x. And then we'll take away 9 from both sides. Seven x equals 1. And then we'll just divide by 7. X equals 1, 7. Okay. So probably our toughest one yet, just because of the properties of exponents. So in my mind, I'm thinking, hey, 3 squared is a 9. You know, and I see this 9 here, and I'm like, okay, so some sort of 2. Well, it turns out that it would just be a -2. Because remember, when you put it a negative, that moves it down to the bottom. And that's how that 9 ends up in the denominator, okay? So the left-hand side can be written as 3 with a -2 exponent. Then the right-hand side, well, we know 3 times 3 is 9. If we add one more 3 on, we get 27. So this is going to be 3 to the third, and I'm going to multiply it by the x because of what we said a second ago, that when you have an exponent on another exponent, it becomes multiplication, right? So 3 cubed raised to the x will become 3 to the 3x. Okay, the bases match, so we'll forget about the 3's. Let's set the exponents equal to each other. So this is a one-stepper here, divide by 3. And now we have that x equals -2/3. So that one was tricky, but anytime you see 1 over, you know you're going to have a negative on your exponent. It's that easy. Okay, now sometimes we can't write logarithms with the same base. I mean, just to give you an example, you know, if you make this guy a 7, well, there's no way for me to write 7 with 2 as its base. And so I can't use the equivalence property that we were using on the last 3 examples. So we'll go through these 4 steps on the next few problems, and I'll mention them every time so that way we kind of get used to them. On a side note, we're going to do the natural logarithm just so that there's something consistent for students. But honestly, you can take any logarithm, but I'm going to go ahead and natural log it. I know a lot of people only have log and natural log on their calculators, and sure they could use to change a base, but just decided to take this path here. Okay, so step 1 is to isolate the exponential. Well, in our case, the exponential has already been isolated. So the next step, go back to step 2, we're supposed to take the natural log of both sides. So we're going to go ahead and natural log both sides. Okay, so we have, now the reason why we're natural logging both sides is so that we can get that x out of the exponent. Okay, we're not used to solving with x in the exponent. Usually x is on level ground with everybody else. Well, once we put a natural log in front, we can use the power property of logarithms to move that x to the front of the log. So that good old power property we just practiced in the last section coming into play here. And then you would solve like you would normally solve. The natural log of 3 is multiplying by the x, so we're going to divide by it. The natural log of 3 is a number, you guys. You have to have something inside the natural log. I have some students who will have an empty natural log, like in this step, maybe they put it over here when I say natural log both sides. You have to be taking the natural log of something. That would be like having an empty square root. There's got to be something that you're square rooting. Well, there's got to be something that you're natural logging. So I squeezed it in front of the 20. And that would just be some number on the calculator, a decimal number, okay? All right, we could leave it like this, but let's also go in and get it approximately, just in case that's what your homework assignment asks for. And we'll do 4 decimal digits. My, got a lot going on here, huh? Okay. So we had natural log of 20. Make sure you close your parentheses, you guys. That's the biggest mistake I see. Natural log of 3. All right, so we'll say 2.7268. There's a 3 here, so we won't round it up. 2.7268. 2.7268. All right, Example B. All right, isolate the exponential. It's done already. So we are at the step where we would natural log both sides. And remember, we natural log so that we can pull. Actually, I don't like writing on top of this. I feel squished. So let me kind of start this over, you guys. Okay, so we're going to natural log both sides so that we can use the power property, which is step 3, to pull the exponent out front. Okay. And we're trying to get x by itself, and everything is multiplying, right? This 0.02 is multiplying by the x, and the natural log of 3 is multiplying by the x. So we're going to divide to get rid of it. We'll cancel this guy out, we'll cancel this guy out, and just the x remains, okay? But whatever you do to one side, you've got to do to the other. So here's our answer. X equals the natural log of 0.07 over negative 0.02, natural log of 3. If we needed to get the approximate, and by the way, this would be exact, right? And the bottom one's the approximate. Let's go to our calculator and put that in. So we have natural log of 0.07, close parentheses, divided by parentheses, negative 0.02, natural log of 3. 121.0281. 121.0281 would be our approximate. I seem to remember my math lab asking for the approximate a lot, so that's why I'm going to that extra step. All right, step 1, isolate the exponential. Well, we can finally do that. The exponential is this piece right there. So we have to get that. It's the thing that's being raised to the exponent. The 3 is not part of the exponential because the 3 is not being raised to that exponent. So we also have to get rid of the 3, you guys. All right, so we're going to start by subtracting 4 to both sides. These will cancel, so we get 3 e to the 2x equals 7. And then that 3 is multiplying, so we're going to have to divide to get rid of it. All right, so now we're going to natural log both sides. That's all of it that's being natural log. And remember, natural log and e are inverse functions, so they will actually cancel each other out, and just the 2x will remain. All right, so our last step is to divide by 2, and we have the x isolated. So you can write it like this. I try to avoid the fraction, right? The fraction within a fraction. So another way to write it, instead of saying divided by 2, you could say take half of it. That might be a little bit cleaner looking for some people. It might be uglier looking. Let's go put this in and see what this becomes. So we have the natural log of 7 divided by 3. And this is all going to be over 2. Okay, 4236. So 0.4236 would be the approximate for this. All right. Okay, so we're going to go ahead. Let me write it here with some space. Oops. So isolate the exponential. They're already isolated. So we're going to take the natural log of both sides to move the exponent in front of the logarithm. So we're going to have 3x minus 2, natural log of 2. And we're going to have 2x plus 1, natural log of 3. Now there's 2 x's, so we can't just go and get one of the x's by itself. So we're going to have to distribute in this case. So let's see, when we distribute, we get 3x natural log of 2 minus 2 natural log of 2. Then on the other side, 2x natural log of 3 plus 1 times natural log of 3. So now we're going to go ahead and get everything that has an x on one side and anything that doesn't have an x on the other. Okay. So here we go. So I'm going to go ahead and move this over. So it will be negative now. So minus 2x natural log of 3. And I'm going to move this one over to the other side because it doesn't have an x. So anything that has an x, I've moved over to the left. And anything that doesn't have an x, I've moved over to the right. Now, the reason why we wanted everything that has an x in it on one side is because if everything here has an x, then we can factor out the x. I'm going to do that parentheses there. So it'll just be 3 natural log of 2 minus 2 natural log of 3. And this is a big moment because it took us from 2 x's down to 1x. So now we can solve this, right? We'll go ahead and divide since we're multiplying. So we're going to divide by this entire thing. It's pretty massive, but that's what we're going to divide by. Okay, so that all cancels. And so look at this answer. Boy, it's a crazy looking answer. Natural log of 3 plus 2 natural log of 2. 3 natural log of 2 minus 2 natural log of 3. Okay. So that's perfectly fine answer right there. Sometimes I like to clean it up a little bit so it's easier to type into my calculator. So another way to write this that's like a little bit neater is to pull all of these numbers in front of the log up to the exponents. Then it'll be a little bit cleaner to write. So if we pull the 2 up to the exponent, 2 to the second is 4. If we pull this 3 down here up to the exponent, it'd be 2 to the third, which is 8. And if we pull this 2 to the exponent, 3 squared is 9. And you can see that this is a little bit simpler to substitute in to a calculator than the other one. So let's go and see what that looks like. Okay. All right, I'll go ahead and get my fraction going. So we got natural log of 3, close your parentheses, plus natural log of 4, close your parentheses. Oops, and then we have natural log of 8 minus natural log of 9. Oops, I guess I didn't put the natural log that time. There we go. Okay, move this guy over here a little bit, and let me just check myself because I know I write stuff wrong. So let me make sure that looks good. 2 to the second is 4, 2 to the third is 8, and 3 to the second is 9. This is looking good. Okay, so negative 21.0973. Negative 21.0973 is going to be our approximately. Okay. That's as hard as it gets, you guys, by the way. That is the toughest, the one where you have to distribute these natural logs inside these parentheses and do all this algebra. It's as tough as it gets. Okay, so we have done u-substitutions in this class in some previous videos, and we're going to use the u-substitution again. Whenever we have a polynomial that's factorable, you'll notice that the trend is that this exponent is always double that exponent. So as soon as you see something where this is a 2x and that's a 1x, factoring might come to mind, okay? But before we do that, I'm going to use that property I mentioned earlier that says that when you have multiplication going on, that it's an exponent on an exponent. Okay, and the reason why I did this Because you're going, what is motivating you to write it that way? Well, I would like to have a bunch of e to the x's here. Because now that I have an e to the x here and an e to the x there, I'm going to go ahead and say, let u be e to the x. So I can rewrite this as u squared minus 8u plus 12, and I can make this look like what I'm used to looking at, right? When I go to factor. Okay, so let's go ahead and factor this then. So let me get my little x here. So we're looking for things that multiply to make 12, but that add to make -8. So it looks like that's going to be a -2 and a -6, because a negative times a negative makes a positive, but a negative plus a negative stays negative. So we're ready to rewrite this as u minus 2 and u minus 6. So we're going to set each piece equal to 0. So we'll move the 2 over, making it a +2. And we'll move the 6 over, making it a +6. Now at this point, you've got to make sure that you put x back, because remember, the original problem had only x's. So we are going to have to put x back. So we're going to use the u-substitution in the other way, right? Okay, so what is u? Well, if we go to the red, we can see that u is e to the x. So we're going to use that again right here. So I'm just going to kind of have some arrows pointing to this. So our next line is going to say e to the x equals 2, e to the x equals 6, and we'll have to solve the exponentials. So we know that we take the natural log of both sides. And remember that natural log and e cancel each other out. So we just get x equals natural log of 2. Same thing over here. Natural log and e cancel each other out. So x equals natural log of 6. So don't forget to put the x back. I'd be tempted to write, I know myself, I'd put 2 and 6 in on my math lab and be like, why is that marking that off, right? No, that's because that's what u is. We have to find out what x is. Okay, so I told you that we would have an equivalence property for logarithms as well. Okay, and it basically kind of says the same thing. If log base b of x equals log base b of y, then it must be that x equals y. In other words, we don't care about the logs. Those equal each other, log base b, log base b. Let's set the arguments of the logarithms, the inside of the logarithms, equal to each other. Okay. All right, so this would be a perfect example. They have the same base. They're both log-based too. So on the next line, we can say, forget the logs. We're just going to go ahead and write 5x minus 1 equals 2x plus 17, and then we'll solve this. So I'm going to subtract the 2x from both sides. So I get 3x minus 1 equals 17. And I'll add 1. And then finally divide by 3. Now with logarithms, you have to check your answer. And basically what you're checking, well, let's talk about that. Okay. You must check your answer with logarithmic equations. So basically what we're checking is that we don't get 0 or negatives. Because remember, when you try to log 0, you're going to get a domain error, okay, or error. When you try to log negatives, any negative, you're going to get the same thing. You're going to get an error. You can only log positive numbers. That's when you're going to get a value out, okay? So we want to make sure that what we're logging is positive. So I'm going to just kind of draw an arrow up here, okay? When checking, make sure you're logging something positive. Oops. Make sure you are taking the log of something positive. Okay. So these are actually easy to check then, because when I can do it in my head most of the time. I'm just taking the 6 back here. and making sure that the answer that I get is positive. So that checks out. And then I'll be taking the 6 and substituting it in here. Okay, we're good to go. 6 works, so we'll go ahead and box it. All right, so this does not fit the bill for our equivalence property of logarithms. It's if log base b of x equals log base b of y, then x equals y. Well, we need to make it look like this, and it doesn't. It actually has 2 logarithms over here. But we just finished a section, boy, that's hard to say, finished a section, where we learned that subtraction of 2 logs can condense into division of 1 log. The first one goes on top, and the second one goes on bottom. So now this does fit the equivalence property of logarithms, right? We have log base 10 of this stuff equaling log base 10 of 2. So on the next line, we can say, okay, forget the logs now, okay? We're going to set the arguments of the logarithm equal to each other. Okay, so to get rid of the fractions, we will multiply by the denominator of x plus 1, cancels here. Whatever you do to one side, you got to do it to the other. So we got 3x minus 4 equals 2x plus 2. I'm going to move the smaller variable to keep things positive. And then we'll add the 4. And don't box it, because like we said, you always have to check. That's the type of things that used to burn me all the time when I was a student. All right, so I'm going to go ahead and take 6 and substitute it in here. So let me write up here that this is the checking, okay? All right, so we've got 3 times 6 minus 4. Well, 18 minus 4 is definitely positive. You don't even have to find the number if you don't want to. If you can tell it's positive, then just stop and be like, cool. All right, and then if we substitute a 6 in there, yes, 7 is positive. So we are going to keep x equals 6 as our answer. Okay, again, this one's going to need to be rewritten. So addition, the last one was subtraction and it became division. So this time addition is going to become multiplication. So we have the natural log of x plus 3 multiplying by x. So now we're allowed to use the equivalence property of logarithms because they're both natural logs. That means they have the same base. They have base e. So we're going to take x plus 3 and we're going to multiply it by x. So if we do that, we get x to the second plus 3x equals 10. Now remember, anytime you have an x squared, most of the time, right, you want to get everybody on one side. So I'm going to move this 10 over, so that way we get that equals 0 that we usually want when we're talking about quadratics. Okay, let's see if there's any factors of -10. So anything that multiplies to make -10 and adds to make 3. Some sort of 5 and 2. I'm thinking the negative on the 2. Yeah, 5 times -2 is -10, but 5 plus -2 is 3. So we're going to go straight to x plus 5, x minus 2. Set each one of these equal to 0 using the 0 product property. So we'll move the 5 over, making it negative. We'll move the 2 over, making it positive. Now, let's go ahead and do our check. Now remember, we're just checking to see if we substitute that number in, if we will get a positive. -5 plus 3 is -2. That means a no for this one, right? Let me put it right here. Okay, so We're going to cross off -5. Oops, I want to make sure you can still read it. There we go. All right, now let's try 2. So if we substitute 2 in right here, 2 plus 3 does get us something positive. And of course, if we substitute 2 in here, we get something positive. So it looks like we're going to go ahead and keep 2 as the answer. Okay. So we got a little bit of rewriting first. We're going to move anything that's in front of a log up to the exponent. So this is going to become log base 3 of x squared. And then we know that addition is going to become multiplication. So we're going to multiply 2 by 3x minus 4. Boy, that sure looks like a y, huh? There we go. Okay, so now we fit the equivalence property of logarithms. So we can get rid of the log portion and just set the arguments x squared equals to 2 times the quantity, 3x minus 4. Okay, so I'm going to go ahead and distribute that too. And then we're going to get everybody on one side. So we're going to move both of these over to the other side, right? So we've got x squared take away 6x plus 8. Got to change their signs when you cross the equal sign. All right. So we're looking for things that multiply to make positive 8 and add to make -6. A negative times a negative would equal a positive, but a negative plus a negative would stay negative. So that is it. So when we set each one of these equal to 0, their signs are going to change and become a +4 and a +2. So let's go in here and check that these are indeed loggable, right? That we would be able to take the logarithm of them. Well, if we substitute, oops, I went off the board here. If we substitute a 4 in there, we're good. Let's check and see if we substitute a 4 in there. And like I said, don't do the math. I do it for your notes' sake. But if you're like, yeah, that's going to be positive, then be done with it, right? Okay, 12 minus 4, that's a keeper. Let's go in and check 2. So of course, if we substitute 2 in here, it'll be positive. Let's check 2 in here. Yes, 6 minus 4 is a positive number. So that one's a keeper too. All right. Guys, this checking is so important because I've seen the multiple choice, and the multiple choice will be like, okay, for A, it's 4 and 2, and you'll box it because that's what you got. And then like back here at D, they'll have like just 2 or something. And maybe that's the case, like maybe 4 doesn't check out, you know, and you'll box this because you'll be like, oh, cool, I got those answers, right? But it turned out 4 didn't work and it should have been D. So just make sure that you're always checking logs. Just lock that in for the test on this section. Logs must be checked. Logs must be checked. Okay, now just like with exponentials, not every single logarithm is going to be able to be written in the form necessary for the equivalence property of logarithms. Sometimes we have a constant in there. Okay, so these are those steps for solving when you have a mix of logarithms with constants. Let me show you what I mean by that. This has a log, but this one doesn't have a log. So this is a mixture of logs and constants. So there's no way we're going to be able to make that look like the equivalence property of logarithms because we need logs on both sides for that. So here's the sequence of steps that you're going to go through to get the job done. So first of all, get all logarithms on one side and all constants on the other. Use the properties of logarithms to condense multiple logs into a single log. So the quotient property, the product property, and possibly the power. Use the hook method to rewrite it as an exponential, solve, and of course, we got to make sure that we check, right? Okay, so step 1, get all logs on one side and all constants on the other. That's done. Step 2, use the properties to condense multiple logs into a single log. Well, we already have a single log. So we're on step 3, which is to use the hook properties. So we're going to say 5 to the second equals 3x plus 1. So remember, you always start with the base, you cross the equal sign to get your exponent, and then you come back. And once we've done that, I mean, gosh, this is easy to solve, right? So back to like week 1 or 2 of class, we got this. So the whole goal here is to get rid of the word log. There should not be the word log when you go in and try to solve. All right, so this is 24 equals 3x. So we'll just divide by 3. And 3 goes into 24 8 times. So x equals 8 maybe. We're going to go ahead and just do our quick check, right? So when we take the 8 and we substitute it in, 3 times 8 plus 1, yes, 24 plus 1 is positive. And so we're going to go ahead and keep x equals 8 as our answer. Okay, we're going to up the difficulty a little bit each time, okay? Get all logs on one side. We've done it. Use the properties to rewrite multiple logs as a single log. Well, we have subtraction here. So these multiple logs are going to combine into a single log using division. The x plus 6 is on the top and the x minus 2 is on the bottom. So we've done step 2. We combined multiple logs into a single log. So now we're ready to do step 3, which is using the hook. So 3 to the 2nd power equals all that stuff. And this is an important step because it gets rid of the log. And that's what makes this really solvable for us, right? Okay, so 3 squared, that's going to be 9. And we know how to get rid of fractions. Multiply by the denominator, or the LCD. And that's what's going to get rid of it here. So we have to distribute that 9 into those parentheses. So we're going to get 9x minus 18 equals x plus 6. So we'll go ahead and subtract x from both sides to get us 8x. And then we will add 18. And then just divide. X equals possibly 3. Let's go see if 3 checks out. Sorry, lost my voice there. Okay, so we're substituting 3 in here. So 3 plus 6 equals a positive number. And we're going to substitute 3 in here. 3 minus 2 equals a positive number. X equals 3 is a valid solution. Okay, get all logs on one side and all constants on the other. So I'm going to move this negative log x over and make it a positive log x. So we actually had to do step 1 this time. Use the properties to combine multiple logarithms into a single logarithm. So these 2 logs are going to combine through multiplication. So we're going to have x plus 15 multiplying by an x. All right, so that's going to get us log of x squared plus 15x. Okay, the base isn't there, so you just got to know that if it's not there, it's a 10. This is the common logarithm. Because now we can use the hook method to say 10 to the 2nd equals x squared plus 15x. Ten to the 2nd is 100. So we'll move that 100 over to the other side. So we get our equals 0. It'll be negative then because we subtracted them over. Okay, so we're going to go ahead and factor. So we need the factors of, let me write the whole equation again just to be clear. So we're looking for the factors of negative 100. So what multiplies to make negative 100, but adds to be positive 15? Okay, I'm kind of a thinker. Let's see here. So negative 10 and 10. 4 times 25. That's not going to get us 15. 5 times 20. There it is. Okay. All right, so -5 times +20 will multiply to make -100, but then those will add up to get you 15. So we got 0 equals x minus 5, x plus 20. Using the zero product property, we're going to set each piece equal to 0. So x equals 5. And when we set x plus 20 equal to 0, x equals -20. The sign changed because we moved it to the other side. All right, we're at the point where we need to check before we go boxing these guys. So let's start off by substituting the 5 in. So 5 plus 15 is definitely a positive number. And then if we put a 5 in there, we're good to go. So now let's start by checking the -20. And right off the bat, it's not good there, right? So -20 is out. So it looks like it's just going to be x equals 5 as the solution. Okay, step 1, get all logs on one side and all constants on the other. So what we're going to do is we're going to move this log over. So we have, oh, the board's doing its thing again. All right, so we have log base 4 of x squared minus 9. And when I move that log over, it'll be a negative log because we would have to, or subtraction, we have to subtract it over. Then we're going to take the 3 over to the other side by addition. And so it's going to be a positive 3. So we got all the logs on one side and we got all the non-logs on the other side. Step 2, condense multiple logs into a single log by using the properties. So we know by the quotient property that subtraction is going to become division. So let's combine these two logs into a single log. And it's going to be x squared minus 9 on top and x plus 3 on bottom. Step 3, use the hook method to rewrite as an exponential. So this is going to be 4 to the power 3 equals x squared minus 9 over x plus 3. So 4 to the third, that's 64. And you might look at that x squared minus 9 and go, hey, that guy factors, difference is squared. So my favorite thing to factor. So it's going to be an x plus 3 and an x minus 3. And the impetus for actually factoring that is seeing that we're going to have a common factor. And now we can cancel that out. So we got 64 equals x minus 3. So our last step is to add 3 to both sides. And that ends up getting us 67 equals x. So we're going to go ahead and check that 67. I don't even want to do the math. Okay, to 67 minus 9, it's something positive, right? So it checks out. Okay. And then if we substitute it in here, 67 plus 3, yeah, that's something positive. So that checks out. So we are going to keep 67 as a solution. I told you the checking would be super easy on these, right? Not a lot of work. I'm used to checking being really long. All right, you guys. So that is it for 5.5. To summarize, we have equivalence properties for both exponentials and logarithms. For exponentials, try to get them to where they have the same base. So if you spot like a 9 and a 3, or if you spot like a 32 and a 2, for example, then write them as the same base, okay? You can get a log to equal another log, cool, then get rid of the words log. That's your equivalence properties. And then we have steps that we have to follow for the other cases where we can't use the equivalence properties. And the main thing to remember with logs, check your answers. I got burned by that myself when I was a student. So don't forget to check on the logarithms. All right, thanks for joining me, you guys. Take care.